Yeah, you can start.
Okay, so I was actually a little bit confused in the whole DHT stuff in the BitTorrent part.
You can ignore it. It's not part of the exam.
Sorry.
You can ignore it. It is not part of the exam.
Okay, okay. Thanks, sir. Then I think
Yeah.
I'll work on that later.
Okay.
Good evening, sir.
Hi, Rohan.
Yes, sir. So actually, I shared the questions I had a doubt in with you.
Hi, Ji.
Did
Hi,
you?
Ji. So
Uh,
let's
yes.
suppose you have a file of size 2.5 TB that you want to store on the HDFS with a block size of 256 MB. How many nodes will the file be replicated on? So this is a question from ChatGPT, right?
Yes, sir.
So this is a wrong question. It is not even giving information about like what uh, how many data nodes are there, or
Right, sir.
what is the storage capacity of each data node. So this is a wrong question basically.
Right.
It's
So
an
that's why I was getting confused. So
mhm.
okay. So there's another one actually.
Suppose
Uh,
you have a Hadoop cluster with 12 nodes and you want to store a file of size 20 GB with replication factor 4. So how many copies of the file will be stored that is equal to the replication factor,
right, sir.
and how many blocks will be the file be divided into? Again, this is an incomplete question because it is not giving you the block size.
Okay. So just to be clear, like the questions we had in the practice questions,
Huh.
while it might not be the exact, but along those lines, yes, that's what we'll be getting in the end, sir.
I mean, so if you are able
Yeah.
to do these questions, so I can't say that they would be exactly similar,
Right, sir.
but if you are able to solve the practice sheet, so questions should be similar to them.
All right, sir. So the other doubt I had was for Raft, for like in the practice questions. So like in Raft, there are questions about I think the total number of messages as well as the majority needed for both of them. So I just go to the practice questions once.
Sure.
So
No, so for Raft, I
yeah,
would suggest you get a clear understanding of what Raft is doing, the tool algorithms, leader election, and how do the synchronization of logs happen across multiple nodes. So just the practice
right,
sheet
sir.
will not be sufficient. So you have to be, so for Raft, 2PC and distributed snapshots, make sure you understand all these three algorithms perfectly. Uh, then only you would be able to answer all the questions. Of course, if you have just done the practice sheet, some questions you might be able to answer, but so basically these three algorithms you need to actually understand, then only you'll be able to answer the exam questions. Otherwise it would be difficult, I think.
Right. So I understand that. It's just that still I do have a doubt in question four of the practice questions. I think
Uh-huh.
you had tried to resolve it also, but I still had a doubt. So I think the question is what is the minimum number of messages exchanged by the leader to commit a log entry in its own log in a Raft
Uh-huh.
cluster with 5 nodes.
Right.
So if you have 5 nodes, one of them is a leader. We
Right.
are still looking at majority as three, right? So n by two plus one.
Right.
So then, in the case that 5 nodes, one is leader and there are four remaining,
Right.
so it needs to get acknowledgements from three.
No, it needs to get acknowledgement from two. So
Okay, that's yeah,
think so basically, so afternoon also I tried to explain this. Let's say you are in a city in which there are five citizens, and there is an
okay,
election going on in which you are the candidate, right?
right.
So if you want to win, how many votes do you need?
I mean, remaining are four, so I need 2 votes in that sense.
Right, so you are also going to
Okay,
vote, so your vote is also
right,
counted. So if you are going to vote and there are total five citizens, then you in total you need three votes. One vote
right.
you can cast yourself to yourself, right? You can cast to
Yes,
yourself, right? So remaining is two, so you just need two more votes. Similarly, when there are five nodes in a raft, in the raft cluster, The majority, 3 nodes from majority. So leader is one of these 3 nodes. So you need 2 other votes.
So that would be in the case of a leader election for sure,
Yeah,
right?
even
That's
for
the
append
logic,
entries also. Append entries,
yeah.
the same logic applies, that the majority of the nodes should agree that this entry can be committed, or this entry, so they have this entry, the latest entry. So majority again means 3 nodes. Therefore, and leader is one of them. So other 2 nodes should agree that this is the latest entry, and as soon as the any other 2 nodes have this latest entry, you can go ahead and commit it, because you are ensuring that 3 nodes out of 5
And go.
have this entry,
Right, sir. I see. Fine, sir. I think it's clear now.
right?
So there's just one more question.
Uh,
So with respect to map reduce, I think there was a practice question again. So I think in question number,
Let me
uh,
open the practice sheet.
yes, sir. So in question number 3, basically,
Yeah, just a sec. Question number 3, map reduce, right?
yes, sir.
So what is your doubt?
Sir, I am not understanding the. So, in case of a combiner and without combiner, so in the case of not having a combiner, the output size remains as it in all cases.
Yes.
And with a combiner, we will always have to look at the question and then, I mean, whatever ratio we've got, that has to be applied.
So whatever ratio is given in the question. So
So, okay,
here with combiner,
right.
uh, the intermediate data is reduced by 60%,
And
right?
we have 40%. Yeah.
So 40% is remaining. So let's say your original intermediate data is 1500 GB. So you multiply it by 0.4, that is 40% of 1500 GB. So the remaining data after you apply the combiner is 600 GB.
Right. So what is the size of the data set here is not really relevant, or like the 3 TB
So
data?
it's a
Okay.
good question. So size of the data set is irrelevant.
Right. So
Even
fine.
the map number of map tasks, number of reduced tasks, all this is irrelevant. No,
No,
this is relevant. So this is relevant.
right.
So total intermediate data generated.
Fine, sir. Fine. I think that was route. So if it's going to stay the same without a combiner, then yeah, that's the route I had. So
So without the combiner, the intermediate data size will remain the same. With combiner,
same.
it will reduce as given in the question.
All right, sir. Understood. Right. Thank you, sir. Thank you so
Okay.
Sir,
much.
the combiner is basically the local reduce step, right?
Yes, yes, yes.
All right.
Sir, can we discuss the blockchain questions? I think there was one slide you had posed some questions.
Which questions?
Uh, 1 second, I will. Like there was one notes here
So
where you
there
had,
was
yeah.
they were not really questions. They were questions which were raised during the course of our class discussion, and uh, we were not able to find convincing answers to those questions. So
Okay,
so
so
so what? So if you have a specific question, we can still discuss it.
like could you open? I will tell you which slide it is.
Sure.
Uh, so it's the lecture 24 last slide only.
Right. So
Yeah, so like let's. I guess we can discuss all of them if it's
okay. So question 1 says, how is the longest chain? So proof of work says that any new block should be added on the longest chain, right? So how does this avoid any risk of attack or change in data? So it doesn't avoid 100%. It just reduces the probability of uh,
because
mod.
the nodes are dependent on the hashes, at least are dependent on each other, right?
That is not the only reason. The So in proof of work, what happens is, if you have to change uh, some node, then you also need to change all the subsequent nodes,
Right.
all subsequent blocks, because they are so each
Hash.
block
Yeah.
is dependent on the hash of the previous block, right? So the longer the chain is, more difficult it would be for an attacker to uh, change all of these blocks, because changing all of these changing each and every block requires a lot of work to be performed. So that is the proof of work algorithm.
Also,
So
there was one notion of cumulative difficulty or something like that.
so that is, so longest, by longest we mean not just in terms of the number of blocks, but in terms of the most. So each block has a difficulty level associated with it. So you add the difficulty level of each block, and that gives you the total cumulative, most cumulative, the total cumulative difficulty of that chain. And then chain with the most cumulative difficulty is selected by any new is selected for is preferred over is preferred for adding a new block.
Right.
Does this make sense? Question
Yep.
one.
Yep. Yep.
So question two, what are some of
Yeah.
the,
That's.
that's fine, right?
Yeah.
So so question three is sort of related to question one. So we, for example, we discuss so many details about the raft algorithm, right? But in blockchain, from whatever limited literature I read, they just argue that you just uh, so each node in the blockchain should just select the longest chain, and eventually everyone will agree on everyone will have the same blocks, or everyone will have the same blockchain eventually. So uh, so essentially the consensus algorithm is very simple here. It doesn't have so many details. So in the class, during the class, we were discussing if we can get some more details on the consensus algorithm, how does it eventually ensure and all that.
In the slides, I think there was something regarding how what a node does when it wants to add a new node to the chain.
Right. So it will solve that puzzle. It will solve that puzzle if it is able to solve the puzzle. So that is the proof of work algorithm, right?
No, no, not exactly that. 1 second. The slide 15.
Slide 15. So just a second. Right. So when a node generates a new block, it broadcasts it to the network. Right. And so this again, right? When so this is just saying when the block is already added to the blockchain, then what do you do? So
Okay.
this is just saying that how do you share this new block which you have generated with the other nodes. It is not really talking about which chain you are selecting and all that.
Sir, can it happen that we have like we have two chains and the index number is the same, but the hash is different?
So this slide is talking exactly
Yeah,
about this.
yeah.
Uh,
So I didn't understand this case exactly.
So here what is going to happen is, so let's say there are two nodes, node 1, node 2. Each of them has generated a new block simultaneously, and they have added in their own blockchains, right? So that is what this longest blockchain concept consensus algorithm says, that they will continue to add new blocks. Eventually it will happen that one of the nodes become has a longer blockchain, and that blockchain will be accepted as the uh, final version, and the other node has to now sync its contents with the longer blockchain. So let's say this was the initial conflict, right? Here you have two blocks, block 72 which is different in node 1, and block 72 which is different in node 2. On the right hand side, let's say now what happens is, node 1 has just node 1 was not able to add another block, but node 2 added another block, right? So in this case what will happen is, so till block 71 node 1's contents are exactly the same, right? So what will happen is, node 1 will now have to copy this blockchain into its own blockchain. So now the question would be, what will happen to this block? So this block, the transactions which have happened in this block, they will be uh, again sent. So what is the something called as, I think, mempool or something. So they will again be available for other nodes or this node to add to a new block. So they will be re-added into this blockchain once this node 1 decides to throw this block away. Does this make some sense, or should I repeat?
No, no, sir. Got it.
Yeah. So essentially, consensus is very simple. In case of conflicts, we just choose the chain that has the longest number of blocks. That's all. And what happens to the to the, so let's say if node 1 is deciding that it should accept node 2's blockchain, what happens to its own blockchain? If the transactions are not already added in the blockchain of node 2, then those transactions will be now added as separate blocks.
Okay, sir. So can you also discuss the consensus or difficulty, slide 24?
So consensus or difficulty, so what this slide is saying is, so for this assumes that we understand what is this difficulty, right? So difficulty is
Number of zeros. Yeah.
number of zeros which the hash should have, right? So here what it is saying is, so there are two constants. One is this block generation interval and difficulty adjustment interval. So what is happening is, see, so this, how many, so the difficulty level, right? What is the current difficulty level? Now, let's say there are 20 nodes and each one of them is working on solving the puzzle. So each one of them could have their own difficulty levels, right? So what this consensus says is that everyone should agree on the difficulty of the block. So what should be the current difficulty level for which they should solve? They should they should solve the puzzle, right? So what it is saying is, so every node, what it does is it keeps track of at what frequency the blocks are being generated. So if the blocks are generated too fast, then the difficulty will be increased. If the blocks are generated too slow, then the difficulty would be decreased. That is all what this is saying. So it measures this rate of block generation using these two constants or two variables: block generation interval, these two constants, and difficulty adjustment interval. So what this says is, so when do you measure this rate of block generation? So you measure this uh, after every these many blocks, difficulty adjustment interval. So this defines how often the difficulty should adjust to the increasing or decreasing network hash rate. So in Bitcoin, this value is 2016 blocks. So what happens is, let's say you start from 0 and then you set your difficulty. Then you let 2016 blocks be added to this blockchain. After 2016 blocks have been added, you now check how much time it took to generate these 2016 blocks. So once you have measured this time, you then so essentially that is the total time you can measure, and then you divide it by 2016 to compute the average time it took to generate a block, and then you compare it with this block generation interval. So if the average time average time it took to generate the block is lesser than the block generation interval, that means the blocks are being generated too often. Therefore, the difficulty level should be increased. Otherwise, it should be decreased.
Okay, sir. Also, another question I had. So the notion of difficulty is just decided by how many zeros we add as the prefix,
Yes,
right?
yes, yes.
So does that make it computationally difficult also?
So there is a math behind it. Even I am also not aware of the full math, but the, let's say, the amount of time it will take or amount of work it is required so amount of work required to find a hash which has 3 zeros in front of it, and the amount of work required to find a hash which has 4 zeros in front of it. So the difference in the amount of work is in the power of 2. So amount of work required to generate a hash of difficulty level 4, the amount of work is 2 raised to power 4, and the amount of work required to generate a hash having 3 zeros in the prefix, that requires 2 raised to power 3 work. So the difference is 2 raised to power 4 minus 2 raised to power 3, and that is what I think this most cumulative frequency is also doing. So
Right.
it is essentially adding these 2 raised to power difficulty level values. So this is not arbitrary. This is actually, so there is a math behind it. how much time it takes to. So this is essentially a brute force algorithm, right? You basically loop around and then try to identify the hash value. So the amount of work required to generate a particular hash of a particular difficulty level, that has exponential, that is exponential in terms of the number of zeros.
Okay. Sir, also the last
Sir,
question.
can we please move on to other topics as well?
Sure. So
Sir,
Shaunab, what's your
I
last
had just
question?
I have one question. Then I
Yeah.
guess we can.
Tell
So
Shaunab.
yeah, the last question you had written: are we trusting the sender of the block?
So that is also, so this we clarified in the next class. So essentially all the transactions are verified using the private key and
Right.
public key. So so we are not trusting, we are basically verifying whatever the sender is sending. We are verifying whether the content in that transaction is right or not.
Okay.
Yeah. So using the public key and private key. Okay. Yeah. So who, any other questions?
Yes, sir, I've
Uh-huh.
written my question in there.
Sure. So just a second. So in Raft, how does a network partition get resolved? Is it part of the algorithm specifications, or is that resolved separately? So the algorithm is designed in such a way that a network partition will. So is your question? Let's say there is a network partition now. So what is your question? Do you want to
Yes, sir, suppose a network partition happens, then
write?
uh, in that scenario, does Raft provide a way to uh, resolve it, or
No, no. So Raft doesn't provide anything specific to resolve the network partition. The algorithm will continue working as is, and so there are multiple possibilities. One possibility is that. So we had discussed this. So let me actually try to open the. So this question is also there in the practice sheet, right?
yes, sir, exactly. I mean, my question was
Raft doesn't do anything special to get rid of network partition. If whenever
okay.
the network partition disappears on its own, then the nodes will be able to interact with each other. So Raft doesn't do
All,
anything to
all
take
right,
care of
exactly.
network partition. Yeah,
That was my question.
yeah.
Thank you.
So yes, yeah, slides are sufficient for blockchain. Uh, Whatever is there in the slides, only that would be asked. Any other questions? No, Mitakshi, you are not audible.
Hello.
Hi.
Sir, in the afternoon we discussed what happens in case of network partition when there are 3 nodes in one part and 4 nodes in the other, and
Uh-huh.
the term keeps increasing. But sir, I read the raft thing today, and
Uh-huh.
it actually exchanges the index of the term of the last entry in the log. It does
Right.
not exchange the current term. So uh, even
I
if
see. So let
yes,
us. So do you want to share your screen and just show us?
so it was actually in the video, but
I see. So yeah, so there's some correction to what we discussed in the afternoon. Is that what you're saying?
yeah, yeah.
Okay. So then you can try to explain and then we can discuss more.
Yeah, okay, sir. So, even if suppose there is a network partition and there are 4 nodes on one side and 3 nodes on the other, the four
Uh-huh.
nodes would continue working as usual if there is a
Right.
leader
Right.
already.
Right.
The 3 nodes would try to elect a leader amongst themselves, and the term would keep increasing, but there
Right.
would be no commits that would be done here.
Right. Right.
So now, if the partition heals
Right.
and these nodes become like a part of the whole cluster again,
Right.
uh, they would receive a message from the leader, but we had discussed that their term would be greater than that of
Ha
the
ha
leader.
ha ha ha.
That would actually not be the case, because
Okay.
the leader would, while comparing, the leader would send the uh, the term and the index of the last committed entry in the log, and that is going to be compared. So the last committed entry in the log of even those three nodes are going to be when the term was when the network partition happened. So even if their term increases, the log is going to be the entries in the log are not going to be there.
So using the log entries, you will, so the three nodes which were not able to elect a new leader, they will essentially what they will do, they will revert their term. What they will do?
Yeah, so they'll update. The leader is gonna remain the same, and it's gonna basically make the logs consistent again, and it's gonna function as it was.
So then the problem here is that how will the terms be reconciled, right? Because some of the nodes have a higher term and the leader has a lower term,
Yeah.
and the other node. So what is possible is, so let's say we take the solution which you are saying. So in that case, the leader has to still update its term
Hmm.
because the terms cannot go back, right?
Yeah. Yeah. So I maybe the cumulative term would be updated, but the log entries would still be um, what the leader had, and that is
So last time also, so in the afternoon also, what we were discussing, so we were just discussing that if uh, the three nodes which are not no longer which have a higher term, they will essentially tell the leader that the leader has a lower term, and the leader will step down. It will wait for a re-election, and the new leader will be among these four nodes which have the most up-to-date log. So the log entries will not be an issue. So whoever becomes the leader, uh, the three nodes will sync up their logs with the new leader, and that would be uh, so that would resolve the situation. So whatever entries were updated, whatever entries were committed in this majority partition, they will get reflected in uh, the the smaller partition also eventually.
Yes, sir. But the thing is, we would not need to wait for the term to increase to more than what the three nodes had. It because we are just comparing the term and the index of the last appended entry
Honey, so that I understand. So I see. So what you are saying is,
in the request vote RPC.
So I guess what I would just like to correct one thing. Maybe the way we compare the last term and the last updated index is that first we look at the last latest term and then the last index. If the latest term is already greater, then that would already be a winner. But if the terms are equal, then we would go ahead and look at the last updated
honey,
index.
but here the issue is that the
So what I mean is that when there is a partition and when a new leader was elected in the other partition, then that new leader would be the leader of the whole system.
no, no. So there is no leader in the new partition, right?
But
The
ultimately
smaller.
they would be one. Uh, when when the heartbeat timeout would be there would be a new leader in the partition,
So
right?
uh, let me log
And
in using my iPad. Just a second, so we can discuss this. So let's take this question towards the end. So let's not keep waiting others. So we'll
Uh,
take this question. We'll
so
discuss this
it's
again.
just it's from a resource only that you provided. Uh, you mentioned lecture 19 in the reading material that contains an illustration. In that, if we look at the log replication part, that contains the whole visualization
Okay,
of
so
this
let's go through
process.
it then. Just a second. Let me share my screen.
So in the taskbar only, you can select the log replication. So
Okay, I see. I see. So Raghav, is this what you're
Yes,
referring to?
yes. So from this part.
So let's see what happens. So here right now, there is no network partition right now. And then let's add a network partition to separate A and B from CDE. So in this case, what is going to happen is, so actually this is different from the case which we were discussing in the afternoon. This is the opposite, but let's see this case also. In this case, node C becomes the new leader, right? And it has a newer term. So this is actually more simpler than the case which Mitakshi was referring to. So we were discussing the opposite case. So in this case, you are right. So in this case, what will happen when the network heals? Node C will continue to remain the leader because it is anyway having a higher term. The other nodes here, they have a lower term. So in this case, it's not a problem. We were considering the other case where the leader.
So here the term is not increasing for the two nodes that are below.
Oh, I see.
Yeah.
That
So it is because so if you go ahead with the illustration, it will be more clear. It is just because there was already a leader, so there was no increase in term.
Ha, Mitakshi. So here there is already a leader, right?
It was just that the three nodes in the other partition didn't get a heartbeat timeout, due to which they had to do election again.
Ha, ha. No, so this is fine. So this is perfectly in accordance with whatever we have discussed till now. So Mitakshi, are you able to see this? Why the term is not changing here? Because the leader is
Yes.
already there, right? So the
Yes.
case which we were discussing, there was no leader.
Oh, okay, okay. I might have missed that discussion. So I have to.
So we are considering the opposite scenario where, so in this case, what is happening is the partition, in one partition, the existing leader, the previous leader is there, and in the new partition, in the majority partition, a new leader is elected, right? But let's say there is a scenario where, let's go back, let's restart, right? So in this case, so let's take a pause here. So what is happening is node B is the current leader, and the network partition separates A and B from CDE. The case which we were discussing in the afternoon, we have to consider a scenario where A, B, C are in one partition and D and E are in the other partition. Okay. So in this case, what will happen? So that case, so let's say if D and E are in one partition and A, B, C are in another partition, then D and E will try to hold election again and again, and they will keep on increasing their term. So does everyone agree on this?
So
Yes,
this
sir.
will only happen if their timeouts are equal, right?
No, no. At least one of them will time out sometime, right?
Yes, sir. But the point, it will not go endlessly, is it is dependent on randomization, which means their timeout at one point will eventually be different, and either D or E will finish their timeout first. So one of them would be the leader.
अरे नहीं भाई, ये TNE majority कहाँ है इनके पास?
Ah, okay, 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 fine.
They don't have the
Okay,
majority.
right, right, right. So it will go endlessly.
So actually, if you're interested, we can see if that animation which we have, if that helps us resolve this. Because there
Yes, sir. Now
actually we
it's
can.
clear. Yeah, I was missing on that thing.
So Mitakshi, what you are saying, it is actually not satisfying that condition where the term has to monotonically increase. You see what I'm trying to say?
Uh,
So what you are saying, Mitakshi, what you are saying is that if A, B, C, A, B, and C are in one partition and D and E are in other partition, D and E will continuously keep on increasing their term. So that we are agreeing,
yes, sir.
right? And when and A, B, C will make progress because they have the majority, right?
Yes, sir.
right? And when the network partition resolves, so then what you are saying is that D and E, so B node, the leader will send an append entries message,
So the
and
request vote RPC is the one that has the last committed entry.
right. So request vote RPC, the way it works is first you check the term. So you're saying before checking the term, you will check the log entry.
No, 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 no. I am just saying that we discussed that even in this case, we
Mhm.
would check the current term of the nodes. For example, these two nodes, for example, their current term would have reached 30, but their logs would have been like committed till term 2 only,
Right,
for example.
right, right.
And the nodes and the nodes that are present above might also have the same term, but they might have a longer list of entries in their uh, log.
No, so the ABC will have an older term. Is that so? Are we agreeing on that?
Yeah. But they'll have an older term. For example, term is 1 and
हाँ
term 1 पे ही partition हो गया था.
हाँ हाँ.
ठीक है. And so नीचे वालों का term जो है वो increase होता रहेगा. बट उनके log में जो term था last appended entry का वो 1 ही होगा ना.
ऊपर वालों का बोल रहे हो, जो ऊपर वाले दो
दोनों
पार्ट.
दोनों के logs में जब उनका
हाँ, दोनों के लॉग्स में कमिटेड का लॉग, कमिटेड का टर्म सेम होगा.
Yeah. So जब भी when the partition heals and the request boot RPC goes through,
हाँ हाँ.
the video of the author said that uh, term and the index of the last committed entry in the request boot RPC is sent, not the current term.
अच्छा. So in as part of the request vote.
Yeah.
I see. So that, हाँ, so that might be the case. So just a second. So so this seems reasonable. So in that case, so let's assume that what you are saying is right. ठीक है. Let's assume what you are saying is right. So in that case, what will happen is D and E will send no. So what happens to the so there are two things happening, right? So the previous leader node B will send an append entries message.
Yes, sir.
So what will happen to that? Will it get accepted or will it get rejected?
It will get rejected because the term is lower, right?
Right, it will
So
get rejected. So then the node B will give up its leadership.
yeah, and it will update its term.
It will update its term. So this we discussed in the afternoon,
Yeah.
right? And then so I guess so basically the only difference is what happens in the case of request vote RPC.
Yeah.
So request vote RPC, in the afternoon we discussed that. So basically what you are saying is ABC. So now let's consider a simple scenario. D and E have the term 20 and ABC were term equal to 1, but node B's RPC append RPC will get rejected. So node B will update its term to 20, right?
Mm.
And the request vote RPC request vote RPC will go from D or E to C, B, A, everyone, right?
Yeah.
So you are saying in the request vote RPC, we are not sending the term of the node, we are sending the term of the latest commit entry.
Yeah.
So let me just double check. So this we can directly check from the paper,
Okay, sir.
right? So just a second.
It might be under the section leader completeness.
हाँ देख लेते हैं. So how do I? So we just need to check what is sent in the request vote RPC. So I think what Mitakshi is saying is, so that these are the arguments which are sent, invoked by candidates to gather votes. So we send the candidate's term, we send the candidate requesting vote, whichever is calling this RPC, and the log details, last log index and last log term, right? And the result is term, current term for candidate to update itself and vote whether the vote is granted or not. On the receiver side, first of all, what is checked is if term is less than current term. So my understanding is, so let's actually go to the section 5.1, right? What is it saying? Section 5.1 is just defining term and all that. So leader 5.2 is leader election.
So one point to make is the logs that we are considering here in the or in all the examples that we have discussed does not include any split vote condition, which means that at least one operation did happen in one of the terms. But the situation we are discussing is when multiple terms didn't have any operation in them. So I guess we haven't discussed any part. What I mean to say is we don't know yet whether entry in the log would make uh, the last index appended or not, incremented or not.
No, actually, sorry, Raghav, I'm not able to understand what you are saying. So let's first clarify what Mitakshi was saying. We'll come back to you. So the only I think difference we have is the only clarification we need is when the request vote RPC is sent, what does the candidate send? Does it send its actual term or does it send the term of the last log entry? Mitakshi, that's the question, right?
Yes, sir.
Right. So here it sends both. So the question is what is it compared against? Right, on the receiver side. Right, Mitakshi?
Yes, sir. Yes.
On the receiver side, first of all, this term is going to be compared with the candidate's term.
Okay.
So I am mostly sure about this, but let's just read through this just to confirm.
So I just wanted to tell that if there is a split vote, will there be an entry in log table or not? Because there is no. Uh,
And you see, log table has nothing to do with elections. So
so
logs.
why I am telling this is because, as Mitakshi mentioned, we are telling the last index of the log table, right? From we are sending what is the last index with our term. I agree that the term would be increased, but the last index would be the same as the previous one, right? Because there was no update in the log table due to continuous split vote election that was going on.
So what you? So actually, just a second. So
Sir,
see, the
there
log
was
has
no.
nothing to do with. I'm
Uh,
100% sure log has nothing to do with election. In
yeah,
the sense
yeah, right,
that you
right.
don't make changes to the log based on what is the result of election. That I'm 100% sure. ठीक है, दो चीजें हैं, तीन चीजें हैं, three things are there. One is leader election, second is log replication, third is safety. So these are the three components of RAF, and these leader election does not impact. So whatever happens in leader election, no changes are made to the log entries.
So, sir, the final log entry would be the same for D, E, A, B, and C, right?
No, A, B, and C have made progress. So they A, B, C have moved ahead. So their log entries have increased.
Right. So, what Mitakshi says is that the log entry would revert back to what D and E had.
So come again, last statement.
So, does Mitakshi means that the uh, newly updated log table would revert back to what the D, E entries had? That is, no progress would be made yet. Was that the point Mitakshi was making?
नहीं नहीं.
Nahi. So see, I understood what Mitakshi is saying. So what Mitakshi is saying is, so look at this basically request vote RPC. This is a summary of request vote RPC. The arguments and results are from the sender side, from the candidate side. So candidate sends its own term, its candidate ID, last log index and last log term. In response, it receives the term which is sent by the receiver, right? And whether vote is granted or not. So on the receiver side, first of all, it is checked if the receiver's term is lesser than, if the candidate's term is lesser than the current term of the receiver, then the request is going to be straight away rejected. So in the afternoon, we discussed that the candidate has a higher term, right? And the leader, the previous leader, which has given up its leadership, has a lower term. So this will not be rejected. It will move on to this second point. But here it will be rejected because the log, the receiver's log, candidate's log is not up to date as the receiver's log,
Okay,
Okay.
yes, yes.
right? So this will be rejected. So let me actually draw a diagram. Let's just clarify this. Let's make sure everyone understands this. So just a second, give me a minute. Huh? So what we were discussing. So let me just quickly, 5 nodes, hai na? So let's actually take these 5 nodes. A, B, C, D, E. Okay. For the sake of A. Okay, so let's consider this case. Node B is the current leader. Okay. So A, B, C, D, E. Right? Node B is the current leader. Term is equal to 1 for all. Okay. Now what happens? There is a network partition. So the animation is considering that A and B. So what the animation is considering? Animation is considering this kind of network partition. So this is very simple. In this case, what will happen is this partition will elect a new leader. So I hope this is straightforward, right? This will elect a new leader. So for example, let's say this node becomes the new leader, or I think the example is considering C becomes the leader. It will increment its term. So everyone will have T equal to 2. They will keep on adding entries into its log, and whenever the partition disappears, this leader will give up. This leader will give up its leadership. It will increment its term and accept this as C as the new leader, right? So this is very straightforward. So इसमें तो कोई doubt नहीं है, right? So now let's consider the other scenario where C is there, T equal to 1 is there, and this is the new leader, this is the current leader. Now what happens? The partition is this. Okay. So in this case, what will happen? These two terms will keep on, these two nodes will keep on playing with each other. They will keep on incrementing their term. So let's say the term has become 15. Okay. So in the meanwhile, let's say these three nodes here, they have increased their logs. So let's say the log index is 5 here, right? Everyone is having log index equal to 5 and term is equal to 1 anyway. This is the latest entry in the log file of ABC all three, right? Here, what is the entry? Just for the sake of simplicity, assume that the log file is empty. So there is no log entry, empty log. Okay. Now let's say the partition disappears. Now what will happen? So there are two things which are going to happen. One is this request vote RPC, right? Second is append entries RPC. So append entries RPC is the job of the leader. So this leader will send the append entries RPC. So let's say, we can consider whatever scenario you want me to consider, but let's consider append entries RPC is sent first by node B to everyone. So node D also receives this append entries RPC. So this is going to reject the append entry RPC because D is having a higher term and B is having a lower term, right? So B will now give up its leadership right? It will become a follower, or it will basically wait for some leader to get elected. Okay. And they will update, B will now update its term to T equal to 15. Right? So now
Sir,
what will
doesn't this happen when election is happening, not while append entries?
so let's no, so this was a, so you're saying during append entries the term cannot change?
I think so.
So let's consider the other scenario, right? So in the
No,
request,
it's fine actually. That the return value by D, it will contain the term of D,
right,
and then the leader, which is earlier leader B, will update its term. It's written in the paper.
right. So even if so Mitakshi, are you saying we should first see what happens to the request vote RPC sent by the D to P?
Yeah, sir.
So let me first consider finish this scenario and then I'll come back to your
Okay,
selected scenario also, right? So in this case, what will happen is T equal to 15, B will update its term, right? And the other terms, for example, let's say they are still T equal to 1. So now what will happen? So what will happen? Let's just rub this, right? Now request vote RPC will be sent by D to everyone, right? It is asking for these votes. So C and A will automatically update their terms because they have received a new candidate vote. I mean, received a request from a new candidate, right? So they will also update their t equal to 15, and just assume that now this is going to become the leader. So this becomes the leader, right? So is this fine, Mitakshi?
Sir, but the, isn't the log entry empty?
Oh,
for
sorry. So I'm wrong. So sorry. So sorry. So you're right. So when the vote, so let's go back. So when the vote request arrived at C, right, they are going to not accept this candidate as the leader because it is having an empty log, and the C, these A, B, C, all three are having a more updated log, even though their term was lesser than D's term, right? So this vote will be denied. So this will be denied, this will be denied, this will be denied, right? So this won't become the leader. So this cannot become the leader, this cannot become the leader because their logs are not updated. So this is reasonable, right?
Yes, sir.
So now what will happen? Any one of these will start contesting the election, right? So then you can assume that, let's say C starts contesting the election. So when C starts contesting the election, C is having the latest term, or actually the term will be further increased, T equal to 16, because in the previous term no leader was elected. So C will increment its term. It will then send the request vote RPC to everyone, right? And I think eventually, so this will be accepted. So all these will accept its leadership, and C will become the leader.
Yes, sir, got it. So, basically, the term can get updated with any sort of request, not just request vote, even with the
Yes.
pent entries.
So that is what I think Shaunak was also asking this question in the afternoon, and we concluded based on our reading of the paper that it doesn't harm in any way to update your term,
Okay, sir, got it.
right?
Yeah.
So now you can consider the other scenario also; it will work exactly the same.
Yeah,
So,
yeah, got
right?
it.
So while I explained, I considered append entries first, and then we discuss request vote. But you can consider the other way around also. First you send request vote, right? In that case also, this request vote sent by D will all be rejected, and then B will also have to give up its leadership because it is having a lower term, and eventually a new leader will have to be elected,
Yes, sir, got it.
right? So yeah, but it's a good discussion. So even see, until unless we actually implement these algorithms, we won't really understand what is happening in these algorithms. So best way to learn anything is to actually implement. Since we have not implemented, I have also not implemented. Some confusion will always be there, but that's fine. So it was a good discussion. So I hope all the doubts are clarified. So Raghav, are you clear with? So you had some questions about craft, Raghav. All right. So should we move forward? Any other questions? Anyone? No questions? Am I audible?
Yes, sir.
Okay. Okay, so then should we end the discussion? Raghav, are you able to hear me? Hello.
Sir, I guess he left the meeting.
Okay. So I guess then we can just close for today.
Yeah, sir. Thank you, sir.
Okay, all right. Thank you. Hi, Raghav.
Yes, sir.
So, Raghav, are your doubts cleared or anything is remaining?
Now it's clear. Yeah.
It's clear?
Yes, sir. Yes, sir.
Okay. Okay. All
Also,
right.
sir, just one small thing.
Uh-huh.
Could you give an idea about whether the pseudo codes would be expected for map reduced
Actually, there's a lot of
written?
disturbance in your voice, so it's very difficult to hear your voice.
Now is it clear?
So, please
Uh,
speak.
Sir, I just had a query whether uh, questions like pseudocode would be
नहीं
expected
नहीं
in
नहीं
map reduce or not.
सूडो कोड नहीं पूछेंगे.
Uh, like we had in CLDC.
No. So we
Okay,
won't
okay.
ask.
Fine, sir, fine.
Okay.
Yes, sir. Thanks a lot, sir.
All right. Thank you.